Welcome back to the deep dive. Today, we are plunging right into uh, really the frontier stuff, quantum computing.
Absolutely.
Now, we hear a lot about the promise, right? Incredible power, solving problems that are just impossible for today's computers. But there's always been this huge catch.
Errors.
Exactly, errors.
Yeah.
It's honestly been the biggest roadblock. But what if I told you Microsoft just announced something? A breakthrough, they claim, cuts these errors down, get this, by 1,000 times.
It's a huge claim, and it tackles the core issue. In quantum systems, you have this constant noise. It causes errors way, way more often than in, the classical bits in your phone or laptop.
And you can't just fix them the same way, right?
Not at all. With classical bits, you can make copies. If one flips, the others tell you the right answer. But qubits? They're delicate. You try to copy one or even just measure it directly to see if it's wrong, and poof.
The quantum state collapses.
It collapses, exactly. So error correction is this uniquely thorny problem. Now, for this deep dive, we're looking at a few sources, a good piece from Life Science, Microsoft's own blog post explaining it, and the actual research papers they put on RSPO.
Okay, so that's our mission today. We're going to unpack how these new 4D codes from Microsoft supposedly crack this massive bottleneck fault tolerance.
That's the dream, right? A quantum computer that can actually run long computations without errors derailing everything.
The Holy Grail, essentially.
We want to figure out what this means for the future and what it means for you listening right now. All right, so let's really get into this error problem. When we say high error rates, we mean really high, don't we?
Oh, yeah. It's like trying to, I don't know, build a complex Lego model while someone keeps randomly swapping pieces or knocking them off the table. That's kind of the level of instability we're talking about.
So how have scientists been trying to deal with this up to now? What's the standard approach?
Well, the typical way involves redundancy, but in a quantum way.
Mhm.
You use a bunch of extra physical qubits.
Think of them as guardians. They're entangled, linked with the important logical qubits that are doing the actual calculation.
The ones holding the data.
Exactly. And the trick is you don't measure the logical qubits directly. That would break things. Instead, you measure the physical guardian qubits.
And they sort of tell you if something's gone wrong with the logical qubit they're guarding.
Precisely. They give you clues about errors without you having to disturb the main computation. It lets the process keep going.
But the sources we looked at say these current methods are, and I'm quoting here, difficult to scale, resource intensive, or both. So it sounds like we need a lot of these guardian qubits for every one qubit doing the work.
That's the problem. You might need hundreds, maybe thousands of physical qubits just to create one stable, reliable, logical qubit.
Wow.
And you have to constantly run these error checking routines. It takes time, takes energy, makes the whole system incredibly complex and bulky. It's been a major barrier to building bigger, more powerful quantum computers.
Okay, so that sets the stage perfectly. Now, Microsoft comes along and says they've, quote, cracked the science behind error correction using these 4D codes. Christus Four over at Microsoft Quantum, she's the one quoted about that 1,000-fold error reduction.
Yes, it's a bold statement.
So what are these 4D codes? How do they work? Is it really four-dimensional?
Well, mathematically speaking, yes. It's a type of geometric code. Imagine trying to map out the quantum processing, the error checking, onto a shape, but a shape that exists in 4 dimensions.
Okay, trying to visualize that, like a hyperdonut or something?
Sort of like that, yeah, a torus in 4D. The key idea is using this complex topology to create a kind of self-correcting quantum memory. It smartly links the sample space where the error checks happen to the operational space where the actual quantum data lives.
And this link is through entanglement.
Through an entanglement, yes, but it's how they structure that entanglement using this 4D geometry that's new. And then there's what they call the novel twist. It's not just using a 4D shape. They actually calculated a specific mathematical twist within that shape's geometry.
A twist? What does that do?
That twist is the clever part. It lets them essentially pack the error-correcting code more efficiently onto the qubits. So the same amount of protective code can cover the system using fewer physical qubit entanglements.
So fewer guardian qubits needed for each logical qubit.
Potentially, yes. Or, put another way, it creates a larger space for the error correction to work without interfering with the quantum calculation itself. It's like they found a way to build error resilience into the structure rather than constantly fighting fires after they start. More proactive.
That sounds like a fundamental shift. And Microsoft is highlighting these big benefits. Fewer physical qubits per logical one, checking for errors in a single go.
Single shot check, yeah, which is faster.
And that headline, 1,000-fold reduction, it almost sounds perfect. What's the catch? Or maybe, what are the next steps? Is this proven technology yet?
That's the important caveat. These results are super exciting, but they were published on ArgSev, the preprint server, just this June. They did run experiments using the code on actual quantum hardware, which is crucial validation.
Okay.
But the papers themselves haven't gone through the formal peer review process yet. That's the next hurdle where other scientists really scrutinize the methods and results. So, groundbreaking potential, but still early days in terms of widespread scientific acceptance.
Right. Context is key. Peer review is a crucial step. Okay, so tackling errors is one thing, but then there's this other problem. Sometimes qubits just disappear.
Yeah, especially in certain types of quantum computers, like those using neutral atoms trapped by lasers' optical tweezers.
So, like, the atom just floats away.
Essentially, yes, the trap might fail, or the atom gets knocked out. And if that atom was your qubit, well, your calculation is ruined.
Okay, so how did the Microsoft team address that? Because the sources mention another technique here.
They do, and this is also pretty neat. They demonstrated the ability to replace a lost atom during the computation, mid-cycle,
Without stopping everything.
without stopping everything.
Yeah.
They use an atomic beam to basically shoot a new atom into the empty spot in the array, effectively replacing the lost qubit on the fly.
And the calculation just picks up where it left off.
That's the idea. They claim this is a first, being able to do this kind of mid-computation replacement without disrupting the ongoing quantum processes. It adds another layer of robustness.
Wow. Okay, so we have these potentially revolutionary 4D codes for error correction, and now this technique for error mitigation by replacing lost qubits. What does this all mean in the bigger picture of quantum computing?
Well, it's incredibly significant if it holds up to scrutiny.
Especially since, wasn't it just a week or so before this, IBM also made a big announcement about error correction, aiming for a useful machine by 2029.
Exactly. IBM announced their progress on June 10th, so you've got these two tech giants making major claims about cracking fault tolerance almost simultaneously, but their approaches seem a bit different.
How so?
IBM's approach is often described as more top-down. They're leveraging their specific custom-built hardware and optimizing error correction for their systems.
Yeah.
Very integrated. Microsoft's 4D code approach seems more bottom-up. They focused on the fundamental mathematics of fault tolerance first. The potential advantage there, according to the sources, is that their method might be more general.
Meaning it could potentially work on different types of quantum hardware, not just Microsoft.
That seems to be the suggestion. It might have other applications beyond the hardware and use cases it was tested on, so potentially a more universal solution, but again, needs validation.
So two different strategies, both aiming for the same prize. Reliable, fault-tolerant quantum computing.
Right, and the paper suggests that if these 4D codes work as described, they could lead to universal fault-tolerant quantum computers. You could get more and more powerful logical qubits using relatively modest numbers of physical qubits, run calculations faster, and achieve that true fault tolerance. It could really accelerate things.
It really feels like we're on the cusp of something major then. So just to wrap up what we've covered, Microsoft's new 4D codes, that clever geometric twist, leading to potentially 1,000 times fewer errors.
A staggering number.
Plus this ability to replace lost qubits mid-calculation. It really seems like they're hitting the biggest obstacles head on.
They're aiming directly at the core challenges, yes.
Mm.
Making quantum computers not just powerful in theory, but actually reliable in practice.
Incredible stuff.
And maybe a final thought for you, our listener, to chew on. If these breakthroughs, from Microsoft, from IBM, wherever they come from, if they really do pave the way for truly fault-tolerant quantum computers, what comes next? What fundamental limits might still exist? And perhaps more excitingly, how do you imagine our world changing when these machines can rely